252 million years ago, Earth came closer to dying than at any other point in its history. Entire oceans collapsed, forests vanished, and nearly all life disappeared in what scientists now call the Great Dying. Tonight, we are exploring the terrifying true story of the Permian Mass Extinction. The lost world before dinosaurs, the deadly chain reaction that changed the planet forever, and the few creatures that somehow survived it all. Before we begin, leave a comment below telling me what city you're watching from tonight. 252 million years ago, long before the first dinosaur ever stepped across the Earth, this planet was already filled with life so strange and successful that it must have seemed permanent. Vast forests stretched across enormous continents under heavy skies, tinted orange by dust and heat. Shallow seas shimmered with reefs built by creatures almost no one remembers now. Massive insects drifted through humid air, thick with the smell of wet vegetation and volcanic soil. Predator and prey had already been locked in evolutionary wars for millions of years. Entire ecosystems had risen, adapted, stabilized, and survived disasters that would have wiped out weaker worlds. And yet, despite all of that age, all of that resilience, something was approaching that would erase nearly everything. Not a war, not a single impact, not one dramatic instant, but a slow planetary collapse so immense that scientists still struggle to fully understand how Earth remained alive at all afterward. What makes the Permian extinction so unsettling is not just that it killed an extraordinary amount of life. It is the possibility that, for a period of time, the Earth itself may have started turning against the organisms living on it. The world of the late Permian did not resemble the modern Earth people imagine today. Nearly all major land masses had fused into a gigantic supercontinent called Pangaea, a colossal stretch of connected land so vast that traveling from one side to another would have crossed deserts larger than modern nations. From space, it would have looked almost unnatural, as if the planet's continents had been pulled together into a single scar stretching across the globe. Around it lay Pangaea, an enormous world ocean darker and deeper than anything humans have ever known. The geography alone created violent climate extremes. Inland regions, far from the moderating effects of the sea, became brutally dry, with temperatures likely swinging between scorching days and cold nights. Seasonal monsoons may have hammered coastal regions, while dust storms swept through the continental interior. Some scientists believe parts of Pangaea were already environmentally fragile, long before the extinction truly began. When ecosystems become too interconnected and dependent on stable climate patterns, even relatively small disruptions can begin triggering larger failures. The Permian world may have been thriving on the surface while quietly approaching a dangerous threshold underneath. And yet, life flourished there in astonishing forms. The Earth belonged to creatures that feel almost alien now because they existed before the familiar age of dinosaurs. Across river valleys and floodplains moved giant amphibians with broad armored skulls. Sail-backed predators like Dimetrodon had already dominated earlier eras, though by the late Permian new reptile groups were taking over ecological niches with increasing efficiency. Among the most feared predators were the Gorgonopsians, carnivorous animals with long saber-like teeth and heavy bodies built for ambush. Some resembled distorted combinations of wolves, reptiles, and big cats, though none of those comparisons fully capture how strange they truly were. They were not dinosaurs. They were not mammals. They belonged to branches of evolution that mostly vanished forever. That may be one of the eeriest parts of this story. Entire dynasties of life disappeared so completely that the modern world retains only faint echoes of them buried in stone. In the oceans, the situation was even more complex. Marine ecosystems had spent hundreds of millions of years evolving into intricate systems, layered with predators, scavengers, reef builders, and drifting microscopic organisms that quietly regulated planetary chemistry. Trilobites, ancient arthropods that had survived multiple earlier extinction events, still crawled along the seafloor in dwindling numbers. Ammonoids drifted through ancient waters in spiraled shells, while massive reefs supported dense communities of marine life. To an outside observer, Earth may have appeared overwhelmingly alive, but abundance can sometimes hide vulnerability. Modern ecosystems show similar patterns. Rainforests, coral reefs, and ocean food chains often appear strongest right before instability begins spreading through them. Stability creates dependence. Dependence creates fragility. And fragility becomes dangerous when a planet starts changing faster than life can adapt. One of the most haunting questions surrounding the Permian extinction is whether warning signs were already appearing long before the catastrophe reached its peak. Geological evidence suggests that environmental stress may have been building gradually. Oxygen levels in the atmosphere could have been lower than today in some periods of the late Permian. Certain regions became increasingly arid. Ocean circulation patterns may have slowed in ways that reduced oxygen in deeper waters. Scientists continue debating how severe these early warning phases really were. But the broader picture feels disturbingly familiar. Ecosystems under pressure do not always collapse immediately. Sometimes they absorb stress quietly for thousands or millions of years before suddenly failing in ways that seem catastrophic and irreversible. The Permian extinction also forces a difficult realization about the history of life. Evolution does not move toward safety. It moves toward adaptation in the present moment. Many Permian organisms were highly specialized for the world they inhabited. Forest systems depended on stable rainfall patterns. Marine organisms depended on balanced ocean chemistry. Large predators depended on food chains beneath them remaining intact. The more optimized a species becomes for one version of Earth, the more vulnerable it may become when Earth itself changes. That possibility transforms the extinction from a simple disaster story into something deeper and far more unsettling. It suggests that the very success of Permian life may have contributed to its inability to survive what came next. The fossil record preserves moments from this lost world with eerie clarity, too. Entire landscapes are frozen in sedimentary layers, footprints crossing ancient mudflats, forests buried by floods, marine beds packed with shells from creatures that vanished forever shortly afterward. Some paleontologists describe certain Permian fossil sites as strangely silent after the extinction boundary appears. Rich ecosystems abruptly give way to barren layers with dramatically reduced biodiversity. In some places, it almost looks as if the planet itself had been emptied. But exactly how fast this happened remains controversial. Earlier theories imagined a sudden mass death occurring almost instantly on geological timescales. More recent evidence sometimes points toward multiple waves of environmental collapse spread across long periods. If that interpretation is correct, then many organisms were not killed in one terrible day. They may have endured generations of worsening heat, poisoned coastlines, collapsing food chains, dying forests, and oceans, slowly losing oxygen before finally disappearing. In some ways, that possibility feels darker than a sudden catastrophe. It transforms the extinction into a prolonged planetary unraveling. The sky above late Permian Earth may already have looked unfamiliar by modern standards. Dust carried across the dry interior of Pangaea could have stained sunsets deep red. Massive seasonal storms likely rolled across open plains with almost no natural barriers to stop them. Insects psed through giant fern forests, while predators moved through dense vegetation under suffocating heat. Some regions may have experienced temperatures so extreme that survival already depended on narrow ecological windows near rivers, coastlines, or wetter uplands. And still, despite those harsh conditions, life continued adapting. That persistence is important because it reminds us how extraordinarily resilient life usually is. The Permian extinction was not terrifying because life was weak. It was terrifying because life was strong and still nearly lost everything. There are moments in Earth's history that challenge the comforting assumption that planets naturally remain habitable once complex life appears. The Permian period may represent one of the clearest examples that habitability is not guaranteed. The systems keeping a planet stable, atmosphere, oceans, climate cycles, ecosystems, geology, are deeply connected. Disturb one hard enough, and the others begin reacting in unpredictable ways. Some researchers have even suggested that the extinction approached a kind of runaway environmental chain reaction, where warming oceans, declining oxygen, greenhouse gases, and collapsing ecosystems amplified each other faster and faster. The exact mechanics remain debated, but the possibility alone changes how this extinction feels. It stops being merely a prehistoric tragedy and starts resembling a warning hidden deep in geological time. What makes this ancient world so compelling is that it existed on the edge of familiarity. The continents were real. The oceans were real. The climate systems obeyed the same physical laws that govern Earth today. Yet the creatures inhabiting that world belonged to evolutionary experiments, mostly erased from existence. It feels close enough to recognize, but distant enough to seem almost dreamlike. A lost Earth beneath the Earth we know now. And perhaps that is why the Permian extinction continues haunting scientists more than a century after its discovery. Not simply because it was the deadliest extinction in history, but because it revealed how thin the boundary between stability and collapse may actually be. Before the catastrophe arrived in full, the Permian world likely looked eternal to the creatures living inside it. Forests still grew, rivers still flowed, predators still hunted, seasons still changed across the giant body of Pangaea. To know nothing about the surface of daily survival would have revealed that the planet was approaching the worst biological crisis complex life had ever faced. But deep beneath Siberia, hidden under enormous stretches of crust, forces were already building that would soon begin reshaping the atmosphere, the oceans, and perhaps the future of life itself. By the late Permian period, Earth no longer looked like a world made of separate continents and distant oceans. Almost every major landmass had collided into a single enormous supercontinent so vast that it changed the behavior of the entire planet around it. This was Pangaea, a landmass stretching from pole to pole, surrounded by one colossal ocean called Pangaea. from orbit. If anyone had existed to see it, the Earth would have appeared strangely unbalanced, as if the continents had been welded together into one giant body drifting through dark water. But what made Pangaea so dangerous was not simply its size. It was the way that size disrupted nearly every natural system that normally keeps a planet stable. Modern Earth survives partly because oceans, currents, winds, forests, and separate continents constantly redistribute heat and moisture around the globe. Pangaea interrupted many of those balancing systems. The deeper scientists study this lost supercontinent, the more it begins to resemble a world built for climate extremes. Along the coastlines, seasonal monsoons may have unleashed torrential rainstorms powerful enough to flood entire regions. But far inland, thousands of miles from ocean moisture, the continent transformed into something almost alien. Endless deserts stretched beneath scorching skies, where temperatures likely swung violently between day and night. Some models suggest interior temperatures may have become brutally hot during summer months, especially in lowland areas where heat accumulated with nowhere to escape. Unlike modern continents broken apart by seas and coastlines, Pangaea trapped enormous amounts of heat inside itself. In many ways, it functioned like a gigantic thermal engine. The center of the continent may have been one of the harshest environments complex life had yet attempted to inhabit, and yet life spread across it anyway. That persistence reveals something fascinating about evolution. Life does not wait for perfect conditions. It expands into whatever space exists, even unstable space. Forests grew along rivers and wetter regions. Reptiles adapted to dry climates. Amphibians clustered around shrinking water systems. Insects filled ecological niches across floodplains and seasonal forests. But underneath that apparent success was a growing problem. Giant continents create giant vulnerabilities. On smaller continents, climate disruptions can sometimes remain regional. On Pangaea, environmental changes had the potential to spread across enormous connected ecosystems with very few barriers to stop them. Drought in one area could destabilize food chains hundreds of miles away. Changes in atmospheric circulation could alter rainfall patterns across entire regions. Fires could burn through ecosystems at almost unimaginable scales. There is evidence that seasonal wildfires became increasingly common in some late Permian environments, leaving charcoal deposits buried in ancient sediments. Those fires may not have been isolated disasters. They may have been symptoms of a world growing progressively drier and more volatile. The geography of Pangaea also altered ocean behavior in ways that scientists still debate today. Around the supercontinent stretched Pangaea, the largest ocean Earth has ever known. Its sheer size created circulation patterns unlike anything in the modern world. Some researchers believe deep ocean waters may have circulated poorly in certain regions, allowing oxygen levels to slowly decline over long periods. Modern oceans depend on mixing systems that carry oxygen-rich surface water downward. But when circulation weakens, deeper waters can begin stagnating. If enough of the ocean becomes oxygen-starved, marine ecosystems start collapsing from below, long before anything visible happens at the surface. That possibility changes how the Permian world feels. It suggests the planet may have already been carrying hidden structural weaknesses before the extinction reached its catastrophic phase. There is something eerie about the idea that Earth's greatest extinction may have partially originated from the normal movement of continents themselves. Plate tectonics usually represents renewal. Continents drift apart, oceans open, mountains rise, ecosystems diversify, but sometimes those same geological forces accidentally create unstable worlds. Pangaea concentrated land, altered climate systems, intensified seasonal extremes, and potentially disrupted ocean circulation, all at once. None of those conditions alone necessarily doomed life, but together they may have created a planet unusually vulnerable to cascading environmental shocks. Some scientists have even proposed that Pangaea reduced ecological resilience simply because species had fewer isolated environments where they could survive local collapses. On modern Earth, separate continents and oceans act like partial fire breaks against extinction. In the Permian world, everything was connected. Connectivity creates opportunity during stable periods. During crises, it can spread collapse. The skies over Pangaea likely reflected these extremes constantly. Inland dust storms may have towered for miles, carrying fine sediments across dry basins and floodplains. Coastal regions experienced powerful storms driven by seasonal heating differences between land and sea. Monsoon systems could have shifted dramatically year to year, creating cycles of flood and drought capable of reshaping ecosystems. Fossil evidence suggests some regions alternated between wet and dry phases repeatedly, forcing life into constant adaptation. This was not a calm world. It was a world balanced on extremes long before disaster fully arrived. Yet, perhaps the most unsettling part is how ordinary that instability may have seemed to the creatures living there. Evolution only understands the present environment. Species adapt to existing conditions without knowing whether those conditions are temporary or dangerous. Animals crossing Permian deserts or hunting along ancient river valleys had no awareness that the structure of their planet itself might already be pushing ecosystems toward instability. Some of the strongest clues about late Permian climate come from the rocks left behind. Thick layers of evaporite minerals indicate intense drying in certain inland regions where water repeatedly evaporated under extreme heat. Ancient dune systems reveal vast desert belts stretching across the continent. Meanwhile, plant fossils show that wetter environments still existed elsewhere, especially near coastal and equatorial regions. Pangaea was not uniformly dead or barren. It was unpredictable, and unpredictability may have been one of its defining features. Large-scale climate swings create ecosystems that survive through constant adjustment rather than long-term stability. That kind of environment can produce resilient organisms in the short term while simultaneously making global ecosystems more fragile overall. One especially fascinating idea involves how Pangaea may have influenced atmospheric chemistry itself. Some researchers suggest that widespread arid regions reduced the planet's ability to absorb carbon efficiently through vegetation and soil systems. If true, Earth may have become more sensitive to greenhouse gases over time. In other words, Pangaea might not merely have been a passive stage where extinction happened. It may have actively amplified the severity of whatever came next. The distinction matters because it transforms the extinction from a simple catastrophe into a chain reaction between geology, climate, atmosphere, and life itself. Everything on Earth was interconnected, and Pangaea sat at the center of that interconnected system like an enormous unstable weight. The scale of this world is difficult to imagine now because modern humanity evolved on a fragmented planet filled with separate continents, coastlines, and oceans. Pangaea erased much of that separation. Some regions stretched so far inland that moisture from the sea rarely reached them. Rivers crossing the supercontinent may have flowed for astonishing distances through semi-arid landscapes before finally reaching coastal basins. Migratory routes for animals likely extended across enormous territories. Seasonal weather patterns affected ecosystems at continental scales. And because the world was connected physically, environmental stress could spread with unusual efficiency. There is a quiet irony hidden inside the story of Pangaea. The supercontinent represented one of the greatest geological unions in Earth's history, yet that very union may have contributed to one of Earth's greatest biological collapses. The same tectonic processes that assembled enormous ecosystems together may also have reduced the planet's flexibility when environmental pressures intensified. It is possible that the Earth of the late Permian had become too interconnected for its own survival. Some paleontologists describe the Permian extinction as less of a sudden apocalypse and more of a systems failure. Pangaea fits disturbingly well into that interpretation. Instead of imagining one giant explosion wiping out life instantly, the picture becomes more complex and more haunting. Climates destabilizing, oceans circulating poorly, ecosystems stretched across vulnerable landscapes, forests burning, inland deserts expanding, atmospheric chemistry slowly shifting, a planet under pressure long before the final collapse became unavoidable. And somewhere beneath the surface of this already extreme world, another force was beginning to rise, deep below. What is now Siberia, enormous volcanic systems were building pressure that would eventually release unimaginable quantities of lava and gas into the atmosphere. Pangaea, with all its climatic instability and interconnected ecosystems, may have been uniquely unprepared for what was coming next. The supercontinent had created a world capable of supporting extraordinary life, but possibly also a world where once collapse began, there would be nowhere left to escape it. If someone had stood on the Earth shortly before the Permian extinction, nothing around them would have looked familiar in the way most people imagine prehistoric life today. There were no tyrannosaurs roaring across open plains, no giant sauropods shaking the ground beneath forests, no birds calling through the sky. The age of dinosaurs had not begun yet. Instead, the planet belonged to creatures that seem almost impossible now. Animals built from evolutionary experiments that flourished for millions of years before vanishing so completely that the modern world barely remembers they existed. And perhaps that is what makes the late Permian ecosystem feel so haunting. It was not a primitive draft of later life. It was its own fully developed world, filled with predators, scavengers, forests, migrations, territorial battles, and survival strategies shaped over immense stretches of time. To the creatures living there, this was not some strange, ancient Earth waiting for dinosaurs. It was simply the world. Across the floodplains and dry river valleys of Pangaea moved animals unlike anything alive today. Some looked partially reptilian, but were not true reptiles in the modern sense. Others carried features that strangely resembled mammals long before mammals properly existed. Evolution during the Permian was branching in directions that later disappeared forever, leaving only fragments behind in fossils and skulls buried beneath desert stone. to. One of the most famous predators of earlier Permian ecosystems was Dimetrodon, often mistaken for a dinosaur because of its massive sail rising from its back. But Dimetrodon lived long before dinosaurs evolved. In fact, it belonged to a lineage more closely related to mammals than to reptiles. That single fact reveals how alien this world truly was. The boundaries modern people use to mentally organize animals had not fully formed yet. Evolution was still experimenting. The giant sail on Dimetrodon remains debated even now. Some scientists believe it helped regulate body temperature by absorbing sunlight during cool mornings and releasing heat later in the day. Others suggest it may also have functioned as a display structure for intimidation or mating. What matters is not just the sail itself, but what it represents. Life in the Permian was already becoming highly specialized. Animals were adapting to extreme climates, fluctuating temperatures, and increasingly competitive ecosystems spread across the enormous body of Pangaea. By the late Permian, however, newer predators had begun dominating many environments. Among the strangest were the Gorgonopsians, carnivores with elongated skulls and saber-like canine teeth that made them resemble distorted versions of wolves crossed with reptiles. Some species grew over 10 feet long and likely occupied the role of apex predators across large parts of the supercontinent. Their movements may have been surprisingly agile compared to earlier sprawling animals. Fossil evidence hints that some could move with partially upright postures, an important evolutionary shift because it allowed more efficient locomotion over long distances. On a hot and increasingly dry world, efficiency mattered. Hunting in the Permian may have required traveling enormous distances across unstable landscapes where water and prey could shift seasonally. These predators lived in ecosystems already shaped by environmental pressure, and their bodies reflected that reality. But predators alone never define an ecosystem. 2. The real foundation of the Permian world existed in the vast diversity of herbivores and smaller organisms supporting everything above them. Massive herbivorous animals like Scutosaurus wandered through certain regions carrying thick armored bodies that probably helped defend against attack. Dicynodonts, strange tusked herbivores with beak-like mouths, became some of the most successful land animals of the time. Many resembled creatures assembled from mismatched evolutionary parts, reptilian bodies, mammal-like jaw structures, turtle-like beaks, heavy limbs built for endurance rather than speed. Some scientists believe Dicynodonts thrived, partly because they were adaptable feeders, capable of surviving in fluctuating environments. That adaptability would become increasingly important as conditions across Pangaea grew harsher. One especially fascinating aspect of Permian life is how transitional many species appear in hindsight. Several groups from this era show early traits associated with mammals, including differentiated teeth, changes in jaw mechanics, and possibly higher metabolic activity than older reptilian forms. It's possible that some lineages were already experimenting with more active lifestyles requiring better temperature regulation and more consistent energy use. If that's true, the Permian world may have been witnessing the earliest stages of biological strategies that would eventually dominate Earth hundreds of millions of years later. But almost none of those pioneering forms survived the extinction intact. Entire evolutionary pathways disappeared before reaching their full potential. The oceans were no less strange. Beneath the surface of Panthalassa and the shallow inland seas lived ecosystems built from organisms that had already survived previous extinctions over unimaginable stretches of time. Trilobites still existed, though their diversity had diminished dramatically compared to earlier eras. 2. These ancient armored arthropods had once dominated marine environments for hundreds of millions of years. By the late Permian, they were survivors from another age, lingering remnants of a much older Earth. Soon they would vanish entirely. The extinction at the end of the Permian would finally erase a lineage that had endured longer than the dinosaurs themselves eventually would. Nearby drifted ammonoids with tightly coiled shells, ancestors of later marine cephalopods that evolved into astonishing diversity after earlier crises. Coral-like reef systems supported dense communities of marine organisms, while giant predatory fish patrolled deeper waters. In many places, the oceans may have appeared overwhelmingly alive. Yet beneath that abundance, subtle warning signs may already have been emerging. Some marine ecosystems show evidence of environmental stress even before the extinction peak. Certain reef systems declined. Oxygen levels in deeper waters may have fluctuated. Ocean chemistry appeared to have shifted in ways scientists are still trying to reconstruct. Marine life often reacts earlier to planetary instability because oceans absorb changes gradually before those changes become obvious on land. The late Permian seas may already have been carrying signals of a coming collapse long before surface ecosystems fully understood the danger. On land, the plant life covering Pangaea created landscapes both beautiful and deeply unfamiliar. Forests of Glossopteris spread across southern regions of the supercontinent. Their seed fern leaves carpeting ancient wetlands and river valleys. Unlike modern flowering plants, these ecosystems belonged to a world before grasslands and flowering forests transformed the planet. The forests of the Permian were darker in character, dominated by ancient plant groups adapted to humid lowlands, seasonal flooding, and unstable climates. Towering conifers appeared in drier regions, while fern-like vegetation filled swamp systems where giant insects moved through dense undergrowth. The atmosphere itself may have smelled different from the modern Earth, thick with resin, damp vegetation, mineral-rich mud, and volcanic gases drifting from distant tectonic activity. And perhaps the most unsettling part of this world is how complete it already was. It is easy to think of ancient Earth as unfinished, as though life was gradually improving toward the modern age. But the Permian biosphere was not incomplete. It had already developed complex food webs, specialized predators, migration patterns, ecological competition, and regional biodiversity shaped over immense periods of evolution. Some groups had existed so long, they probably seemed permanent from a geological perspective. That illusion of permanence matters because extinction events rarely arrive in worlds that appear weak. They arrive in worlds that appear stable. The Permian ecosystem was not collapsing because life had failed. It collapsed while life was still thriving across enormous portions of the planet. In fact, that success may have hidden how fragile certain systems had become underneath. Highly interconnected ecosystems can appear incredibly resilient while actually depending on delicate environmental balances. The more optimized organisms become for one version of Earth, the harder it becomes for them to survive rapid planetary change. Calm 2. There is also growing discussion among scientists about whether some late Permian species were already adapting to worsening environmental instability before the extinction fully accelerated. Certain animals appear to have shifted into burrowing lifestyles. Others developed body structures suggesting increased heat tolerance or drought adaptation. Fossil distributions hint that ecosystems were reorganizing in response to changing climates across Pangaea. But adaptation has limits. Evolution works across generations, while planetary crises can move unpredictably fast once feedback systems begin intensifying. That mismatch between biological adaptation and geological catastrophe may have sealed the fate of countless Permian species. Some survived regional droughts, some survived predators, some survived climate swings lasting thousands of years. But very few were prepared for a world where oceans, atmosphere, climate, and ecosystems all began changing together. And still, for a brief period before the collapse truly accelerated, the Earth remained astonishingly alive. Rivers still cut through floodplains crowded with reptilian herbivores. Predators still hunted beneath dim red sunsets, glowing through dust-filled skies. Insects hummed through forests older than almost any ecosystem humans could imagine. Marine creatures drifted through ancient reefs beneath warm, shallow seas. The world had not gone silent yet, but somewhere beneath Siberia, deep within Earth's crust, forces were building that would soon begin pushing this already extreme world beyond the limits of what even resilient life could survive. Far to the north of Pangaea, beneath landscapes that would one day become Siberia, the Earth itself was beginning to fail in a way almost impossible to imagine on a human timescale. Deep below the crust, enormous reservoirs of molten rock had been building pressure for millions of years. The planet's interior was never truly stable. Continents drifted because of it. Mountains rose because of it. Oceans opened and closed because of it. But near the end of the Permian period, something extraordinary happened. The forces moving beneath the surface did not remain buried. They broke upward into the world above with a scale so immense that even today, scientists still debate whether Earth has ever experienced anything more destructive. The region now known as the Siberian Traps began erupting in one of the largest volcanic events in planetary history. Not a single volcano, not one dramatic mountain exploding into the sky. This was something vastly larger and stranger. The crust itself split apart across huge areas, releasing enormous floods of lava through giant fissures that may have stretched for miles. Imagine entire landscapes glowing red at night, while rivers of molten rock rolled across the ground for centuries at a time. Forests igniting far beyond the visible horizon. The air thick with ash and toxic gases. And worst of all, there may not have been silence between eruptions. Some geological evidence suggests these events occurred in repeated pulses over extremely long periods, meaning parts of the world could have remained volcanically unstable for hundreds of thousands of years or more. That possibility changes the emotional weight of the extinction completely. This was not a sudden explosion that ended life overnight. It may have been a planet entering a prolonged state of environmental collapse with almost no recovery time between disasters. Today, the Siberian Traps still exist as enormous volcanic rock formations covering vast regions of northern Asia, though erosion has reduced them dramatically over time. At their peak, the lava flows may have covered millions of square miles. Some estimates suggest enough lava erupted to bury entire modern countries beneath layers of rock hundreds of feet thick, but the lava itself was probably only part of the danger. In many ways, the gases released into the atmosphere may have been far deadlier than the eruptions viewers usually imagine when thinking about volcanoes. Carbon dioxide flooded into the air in staggering quantities. Sulfur dioxide likely darkened the skies and contributed to acid rain. Other gases, including methane released indirectly through heated sediments, may have amplified warming even further. The Earth was not simply being burned from below. Its atmosphere was being chemically altered. One of the most disturbing aspects of the Siberian eruptions is how many different environmental systems they may have disrupted simultaneously. Large volcanic events can initially cool a planet by filling the atmosphere with particles that reflect sunlight. But over longer timescales, greenhouse gases trap heat and drive temperatures upward. Some researchers believe the Permian extinction involved both phases at different times. Short-term volcanic winters, followed by intense global warming. If true, ecosystems may have been repeatedly thrown between radically different climate conditions faster than they could adapt. Forests, already stressed by drought and instability, suddenly faced acid rain and falling temperatures. Then later came extreme heat. Oceans absorbed carbon dioxide and began changing chemically. Atmospheric oxygen levels may have declined further in some regions. It was not one problem. It was a chain reaction spreading through the entire Earth system. The geography of Pangaea made everything worse, because the supercontinent already experienced climate extremes. Many ecosystems were operating close to environmental limits before the eruptions intensified conditions further. Heat trapped inland became even more severe. Rainfall patterns shifted unpredictably. Rivers dried or changed course. Some climate models suggest parts of the tropics may eventually have reached temperatures difficult for many complex organisms to survive consistently. And unlike earlier environmental crises, this catastrophe was global. There were fewer isolated regions where ecosystems could escape long-term disruption. The planet had become interconnected in exactly the wrong way, at exactly the wrong time. There is something almost terrifyingly mechanical about how the extinction appears to unfold in the geological record. The eruptions release greenhouse gases. Temperatures rise. The oceans warm and lose oxygen. Marine ecosystems weaken. Forests collapse. Soil erosion increases. Carbon cycles destabilize further. More greenhouse gases enter the atmosphere. Each stage amplifies the next. Scientists sometimes describe these processes as feedback loops. The term almost sounds too clean for what was happening. In reality, Earth may have been slipping into a state where natural stabilizing systems stopped working effectively. The planet was no longer correcting imbalance fast enough to protect the life living on it. One especially important possibility involves underground coal and organic deposits beneath Siberia. As magma intruded into these carbon-rich sediments, it may have released enormous additional amounts of carbon dioxide and methane into the atmosphere. Some researchers suspect this secondary release dramatically accelerated warming beyond what the eruptions alone could explain. If correct, then the extinction was not caused by lava covering the world directly. It was caused by Earth's internal systems, triggering atmospheric and oceanic collapse indirectly. That distinction matters because it makes the event feel less like a simple natural disaster and more like a planetary systems failure. Life was not merely overwhelmed physically. The conditions required for stable ecosystems were being dismantled piece by piece. Acid rain may have fallen across huge portions of Pangaea as sulfur compounds mixed with atmospheric moisture. Lakes and rivers likely became chemically stressed. Forests already weakened by heat and drought may have died in enormous waves, leaving landscapes exposed to erosion. Fossil evidence from some regions suggests sudden increases in fungal activity after massive plant die-offs, leading to what scientists sometimes call fungal spikes in the geological record. Imagine entire forests collapsing across continents, while strange fungal growth spread through dead ecosystems beneath dim volcanic skies. The atmosphere itself may have looked increasingly hostile. Ash clouds drifting across the sun, blood-red sunsets caused by airborne particles, a constant haze over distant horizons. For animals trying to survive inside those environments, the world would have become progressively less predictable generation after generation. And still, life did not disappear immediately. That detail is important because it reveals how resilient ecosystems usually are. Species migrated, some adapted temporarily. Rivers still flowed in certain regions. Some forests endured longer than others. Certain marine ecosystems held on while nearby areas collapsed. The extinction spread unevenly through time and geography. That unevenness makes the Permian event feel disturbingly realistic compared to cinematic disaster scenarios. Real planetary collapse is rarely clean or simultaneous. It moves through systems gradually, accelerating as stability weakens. Some areas become unlivable first, while others continue functioning for surprisingly long periods. That staggered collapse may explain why the fossil record sometimes preserves moments of apparent normality close to extinction boundaries. Life kept trying to survive, even while the planet beneath it transformed. The oceans may have experienced some of the worst consequences. Warm water holds less oxygen, and evidence suggests vast marine regions became increasingly depleted over time. In oxygen-poor conditions, certain bacteria capable of producing hydrogen sulfide can expand dramatically. Hydrogen sulfide is highly toxic to most complex life. Some scientists have proposed that parts of the Permian Ocean may have begun releasing these poisonous gases into the atmosphere itself. If that occurred at large scales, coastlines could have become deadly environments where poisoned air drifted inland from stagnant seas. The idea remains debated, but the possibility alone is horrifying. Entire marine ecosystems suffocating beneath overheated waters while toxic gases rose toward the surface. There are even hypotheses suggesting the ozone layer may have weakened during parts of the extinction due to atmospheric chemical reactions triggered by volcanic emissions. Increased ultraviolet radiation could then have added further stress to both marine plankton and terrestrial ecosystems already struggling to survive. None of these mechanisms operated in isolation. That is what makes the Siberian eruption so uniquely frightening. They may have triggered multiple overlapping crises at once: warming, acidification, oxygen loss, poisoned oceans, collapsing forests, altered rainfall patterns, atmospheric instability, and food chain disruption, spreading through nearly every ecosystem on Earth. And because the eruptions likely continued for immense spans of time, the planet may never have had an opportunity to stabilize before the next wave of disruption arrived. Some scientists argue over whether the eruptions alone fully explain the severity of the extinction. Alternative theories still exist, including methane bursts from ocean sediments or additional environmental triggers not yet fully understood. But even among competing interpretations, the Siberian traps remain central to nearly every serious reconstruction of what happened. The timing aligns too closely. The environmental consequences fit too much of the evidence, and the sheer scale of the eruptions is almost beyond comprehension. This was not merely volcanic activity. It was one of the rare moments in Earth's history when the interior of the planet violently reshaped conditions at the surface faster than life could respond. And perhaps the most unsettling realization is that many organisms living through the early phases of this catastrophe may not have understood they were already trapped inside an extinction event. Predators still hunted weakened prey across dusty floodplains. Insects still moved through dying forests. Marine animals still drifted through increasingly oxygen-starved seas. Life continued because life always continues for as long as it can. But beneath the surface of that persistence, the Earth had already begun changing into something far more hostile than the world those species evolved to survive. Long before the land fully understood what was happening, the oceans were already beginning to fail. At first, the change may not have looked dramatic from the surface. Waves still rolled across coastlines. Marine creatures still drifted through shallow seas beneath dim sunlight. Coral-like reef systems still stood in warm waters that had supported life for millions of years. But underneath, in the darker layers of the ocean, where sunlight never reached, something dangerous had begun spreading silently across the planet. The deep waters were losing oxygen. That detail sounds almost simple when spoken aloud, but oxygen in the ocean is not just another environmental factor. It is one of the invisible foundations supporting nearly every complex marine ecosystem. Once it begins disappearing at large scales, entire food chains start weakening from the bottom upward. Permian oceans may have entered a state where huge regions slowly became unable to support the life they once carried with ease. And unlike storms or volcanic eruptions, this kind of disaster moved quietly. No explosion marked the beginning. No single moment warned the world that the seas themselves were turning hostile. The warming caused by the Siberian eruptions appears to have pushed ocean systems toward instability faster than many organisms could adapt. Warm water holds less dissolved oxygen than cooler water, and as global temperatures rose, the oceans became increasingly stratified. Surface layers heated, while deeper waters stopped mixing properly with oxygen-rich currents above. Modern oceans still depend on constant circulation to remain healthy. Cold water sinks, oxygen moves downward, nutrients rise upward, and life survives because the system remains in motion. But in the late Permian, that circulation may have slowed dramatically across vast regions of Pangaea and inland seas. Some deep waters became stagnant for extremely long periods, and when oceans stagnate, strange things begin happening beneath the surface. Evidence preserved in ancient sediments suggests enormous portions of the ocean floor may have turned anoxic, meaning almost completely deprived of oxygen. In those environments, normal marine life struggles to survive, but certain bacteria thrive. Among them are microbes capable of producing hydrogen sulfide, a toxic gas lethal to most complex organisms. Today, small oxygen-depleted zones exist naturally in some marine regions, But during the Permian event, the scale may have been almost unimaginable. Entire marine basins could have transformed into poisoned environments where black mud accumulated beneath lifeless waters. Some scientists believe hydrogen sulfide-producing bacteria spread so aggressively that toxic gases may even have reached the atmosphere in significant amounts. If true, coastlines near stagnant seas might have smelled of sulfur and decay, while invisible poison drifted inland from dying waters. The idea remains debated, but it reveals how extreme conditions may have become once ocean chemistry destabilized. Marine ecosystems do not collapse evenly. The strongest species sometimes survive longest, while the most specialized organisms disappear first. During the Permian crisis, reef systems appear to have been among the earliest major casualties. Reef ecosystems depend on extraordinary balance, stable temperatures, healthy chemistry, adequate oxygen, and interconnected food webs. Once those conditions shift beyond certain thresholds, reefs can unravel surprisingly fast. Fossil evidence suggests many late Permian reef communities vanished almost entirely. Structures built over immense periods by countless marine organisms disappeared from the geological record, leaving gaps that would persist for millions of years afterward. It was not merely the loss of individual species. It was the destruction of entire living architectures supporting thousands of ecological relationships simultaneously. One of the creatures caught inside this collapse was the trilobite, an animal so ancient that it had already survived previous extinction events separated by hundreds of millions of years. Trilobites had existed long before the first forests appeared on land. They survived shifting continents, changing climates, and multiple biological crises that erased countless other lineages. By the late Permian, their diversity had declined, but they still endured in marine ecosystems across the world. Then the oceans changed beyond what even they could survive. Permian extinction finally erased the trilobites completely. That detail carries a strange emotional weight because it reveals how deep the crisis truly ran. When a lineage capable of surviving nearly 300 million years suddenly disappears forever, something fundamental has broken inside the planet's systems. And trilobites were not alone. Brachiopods collapsed in diversity. Many ammonoid groups vanished. Entire families of marine invertebrates disappeared from ancient seas that had once seemed biologically unstoppable. Some fossil beds from the extinction interval are almost disturbing in their emptiness. Rich marine ecosystems packed with shells and biodiversity suddenly give way to layers containing very few surviving species. It can feel as though the oceans themselves are falling silent in slow motion. What makes the Permian marine collapse especially frightening is that it may not have involved only heat and oxygen loss. Ocean acidification likely played a major role as well. As volcanic carbon dioxide entered the atmosphere in enormous quantities, the oceans absorbed much of it. This changed seawater chemistry, making it more acidic over time. Organisms dependent on calcium carbonate shells or skeletal structures suddenly faced conditions where building and maintaining those structures became increasingly difficult. In modern oceans, scientists already observe coral reefs and shell-forming organisms reacting to changing chemistry. The Permian event may represent the most extreme ancient example of that process ever recorded. Marine organisms were not merely overheating or suffocating. The chemistry of the water itself was becoming hostile to the structures many species depended on for survival. Some researchers have proposed that portions of the ocean may even have changed color during the worst phases of the extinction. In oxygen-poor environments dominated by certain microbial populations, waters can take on green, purple, or reddish hues depending on bacterial activity and chemical composition. It is possible parts of the Permian Ocean looked profoundly unnatural by modern standards. Vast stagnant waters beneath hazy volcanic skies, coastlines stripped of thriving reef systems, deep basins filled with dark oxygen-starved water where only microbial life flourished. The visual transformation of the planet may have been as unsettling as the biological one, and because the oceans regulate climate, atmospheric chemistry, and nutrient cycles, their decline intensified problems everywhere else. The Earth system was unraveling from multiple directions simultaneously. One especially haunting aspect of marine extinction is how invisible it often remains until collapse becomes unavoidable. On land, dying forests and mass animal deaths create obvious warning signs. In the ocean, decline can spread quietly beneath the surface long before coastal ecosystems visibly fail. Entire populations may weaken gradually as breeding success drops, food chains destabilize, and oxygen levels shift. 2. By the time visible collapse reaches shorelines, the deeper systems supporting life may already be irreversibly damaged. The Permian oceans may have spent thousands of years moving toward catastrophe before the full scale became apparent. That possibility changes the emotional rhythm of the extinction. It stops feeling like a sudden apocalypse and starts resembling a prolonged suffocation of the planet itself. Some areas likely remained habitable longer than others. Shallow, oxygen-rich regions may have temporarily acted as refuges for surviving marine species. Certain organisms, capable of tolerating heat or low oxygen, probably expanded while more sensitive species vanished. But resilience has limits when multiple environmental pressures intensify together. Food chains weakened from below, predators lost prey, reef ecosystems collapsed, plankton populations fluctuated unpredictably, nutrient cycles destabilized. Once those processes begin interacting, recovery becomes incredibly difficult because each damaged system weakens the others further. There is also evidence that the extinction unfolded in waves rather than a perfectly smooth decline. Some marine communities appear to recover slightly before collapsing again under renewed environmental stress. That pattern suggests the oceans were not simply dying once. They were repeatedly destabilized as volcanic activity and climate feedback loops continued altering conditions. Recovery became impossible because the planet never stopped changing long enough for ecosystems to stabilize. The deeper scientists study the Permian extinction, the more it resembles a chain reaction crossing thresholds one after another. Heat weakened circulation. Weak circulation reduced oxygen. Reduced oxygen altered microbial populations. Microbial changes affected atmospheric chemistry. Atmospheric changes intensified warming. Warming accelerated acidification. Each stage amplified the next until the oceans became hostile to much of the complex life they once supported. And perhaps the darkest realization hidden inside this story is that the oceans were usually Earth's most stable environment. Marine ecosystems had survived asteroid impacts, climate shifts, and geological transformations over immense spans of time. The sea was where life itself began. It endured crises that devastated land ecosystems repeatedly throughout Earth's history. But during the Permian extinction, even the oceans approached collapse, not just isolated coastlines or regional habitats, but potentially global marine systems operating at planetary scale. That is what makes this extinction feel so different from ordinary disasters. The Earth was not merely experiencing environmental stress. It was approaching the limits of what its biosphere could tolerate. And while marine ecosystems suffocated beneath warming, poisoned waters, conditions on land were also becoming increasingly hostile. Forests weakened, temperatures climbed higher, rivers changed, fires spread. The collapse that began beneath the oceans was preparing to move fully onto the continents themselves. As the oceans weakened beneath overheated, stagnant waters, the land above was entering a different kind of nightmare. The atmosphere itself was changing, not gradually in the slow geological rhythms life usually adapts to, but fast enough that ecosystems across Pangaea began losing the stability they had depended on for millions of years. The sky over the late Permian world may have looked increasingly unfamiliar even before the worst phases of extinction arrived. Volcanic gases drifting from the Siberian eruptions spread across the atmosphere in enormous quantities. Ash and aerosols dimmed sunlight at times, while greenhouse gases trapped heat at others. The climate did not simply become warmer. It became unstable, and instability is often more dangerous to ecosystems than any single temperature increase, because life can adapt to harsh conditions more easily than to conditions that keep shifting beyond expectation. In some regions of Pangaea, temperatures may have climbed to levels difficult for many large organisms to survive consistently, especially inland, where heat accumulated across the vast supercontinent, with little ocean influence to moderate it. Certain climate models suggest tropical land temperatures may have approached or exceeded thresholds, dangerous for complex animals during extended periods. The exact numbers remain debated, but the broader pattern is difficult to ignore. The Permian Earth was becoming dangerously hot, and unlike modern humans, the creatures living there had no technology, no migration infrastructure, no artificial shelter systems. Survival depended entirely on whether biology itself could adapt quickly enough. The forests were among the first major casualties on land. Trees and dense plant systems rely on surprisingly delicate environmental balances. Rainfall patterns, soil stability, seasonal cycles, atmospheric chemistry, and temperature all interact constantly beneath the surface of a functioning ecosystem. Once volcanic emissions began disrupting those systems simultaneously, entire forest regions may have started weakening long before they fully died. Some fossil records show sharp declines in certain plant communities near extinction boundaries. In other places, forests appear to collapse suddenly and are replaced by signs of erosion and barren sediment layers. Massive root systems that once held soil in place disappeared. Rivers carried increasing amounts of sediment through dying landscapes. Floodplains destabilized, and because plants sit at the base of terrestrial food chains, their decline spread outward into every animal population connected to them. Herbivores lost stable food supplies. Predators lost prey. Ecosystems that once appeared permanent began fragmenting into isolated pockets of survival, surrounded by environmental stress. Wildfires may have become increasingly common as temperatures rose and forests dried. Charcoal deposits preserved in Permian rock layers suggest large-scale burning events occurred repeatedly across parts of the supercontinent under hot, dry conditions. Even a lightning strike could ignite enormous regions of vegetation. Once forests began burning at large scales, they added even more carbon dioxide to the atmosphere, intensifying warming further. This is one of the darkest aspects of the extinction. The planet was no longer experiencing separate disasters. The disasters were feeding each other. Heat created fires. Fires increased greenhouse gases. Greenhouse gases increased heat. Dying forests weakened atmospheric regulation. Weakening ecosystems became less capable of stabilizing climate. The Earth system was beginning to amplify its own collapse. The air itself may have become difficult to tolerate in some regions. Sulfur dioxide, released by volcanic activity, mixed with atmospheric moisture to form acid rain, which likely damaged freshwater systems and weakened vegetation across enormous areas. Imagine rain falling through hazy skies onto already stressed forests, slowly altering soil chemistry and poisoning vulnerable ecosystems. Some lakes and rivers may have become increasingly acidic, further pressuring species already struggling with heat and food instability. The late Permian atmosphere was not simply warmer than before, it was chemically harsher. And because atmospheric systems connect the entire planet, there was no isolated refuge untouched by these changes forever. One especially disturbing possibility involves the ozone layer. Some researchers believe volcanic emissions and atmospheric Maxwellic reactions during the extinction may have weakened ozone protection significantly. If true, more ultraviolet radiation from the sun would have reached the surface of the Earth. Fossil evidence from some plant spores and pollen grains shows signs of damage that certain scientists interpret as possible UV stress. The idea remains debated, but if the ozone layer was compromised, the consequences would have spread through ecosystems already pushed close to collapse. Plants damaged by increased UV radiation become weaker and less productive. Marine plankton near the surface struggle to survive. Food chains destabilize further. Even sunlight itself begins turning hostile. The deeper scientists study the Permian extinction, the more it resembles a world where multiple life support systems failed together. And still, not every region died immediately. That is what makes the story feel so real. Even inside collapse, life kept trying to reorganize itself. Some drought-resistant plants spread into areas where forests disappeared. Certain small animals capable of burrowing or tolerating heat survived longer than larger specialized species. Rivers still carried water in some regions, while nearby basins turned dry and hostile. The extinction was uneven because planetary collapse is rarely symmetrical. Some ecosystems fail first, while others temporarily endure under narrowing survival windows. But those windows continued shrinking. One of the most haunting details about the late Permian climate is how exhausting survival may have become even before extinction reached its peak. Large animals generate enormous body heat and depend on stable access to water and food. In increasingly hot climates, simply moving across exposed terrain can become physiologically dangerous. Heat stress affects metabolism, reproduction, migration, and predator-prey relationships simultaneously. Predators become less efficient hunters. Herbivores struggle to travel long distances. Pool water sources shrink or fluctuate unpredictably. Modern ecosystems already show how sensitive large animals are to prolonged heat waves and drought conditions. Permian world was facing those pressures at planetary scale over immense periods of time. Some scientists suspect tropical regions may eventually have become nearly uninhabitable for many large land species during the worst intervals of warming. If accurate, entire ecological zones could have collapsed simply because temperatures crossed biological survival thresholds too often. The concept sounds abstract until it is imagined physically. A predator standing beneath a dim red sky, unable to cool its body efficiently. Rivers reduced to shrinking channels beneath cracked floodplains. Forest canopies thinning year after year. Seasonal migrations breaking down because traditional feeding grounds no longer support life consistently. Generation after generation born into a world slightly harsher than the one before it. Extinction does not always arrive as sudden death. Sometimes it arrives as the gradual disappearance of conditions required for ordinary survival. The atmosphere during this time may also have carried enormous amounts of dust and aerosols from both volcanic activity and expanding dry regions across Pangaea. Sunsets could have glowed deep orange or blood red beneath thick, hazy skies. Too, some regions may have experienced prolonged dimming from airborne particles, temporarily cooling local climates before greenhouse warming overwhelmed those effects later. The weather itself likely became increasingly unpredictable. Powerful storms, driven by heat imbalances, may have swept across exposed landscapes, while other regions endured prolonged droughts lasting years. 2. The climate systems regulating the planet were no longer stable enough to support long-term ecological balance. There is an unsettling irony hidden inside this stage of the extinction. Earlier in Earth's history, life had survived massive volcanic events, climate shifts, and atmospheric fluctuations before. But the late Permian combined too many crises at once. Warming alone might not have destroyed the biosphere completely. Ocean oxygen loss alone might not have done it either. Forest collapse, acid rain, wildfires, UV stress, toxic gases, changing rainfall, food chain instability, and atmospheric disruption together created something much harder to survive. The extinction became dangerous, not because one environmental factor turned lethal, but because every survival system organisms depended on began weakening simultaneously. This is why the Permian extinction still disturbs scientists so deeply. It reveals how interconnected planetary habitability really is. The Earth does not remain stable because any single system protects it. Stability emerges from countless systems, balancing one another constantly. Once enough of those systems fail together, even a biologically rich world can begin moving toward collapse surprisingly fast. By this stage of the Permian crisis, many ecosystems may already have passed points where full recovery was realistically possible. Species continued surviving locally, but the broader structure supporting biodiversity across the planet was unraveling. Forests no longer stabilized climate the same way. Oceans no longer circulated oxygen effectively. Food chains no longer operated reliably. The atmosphere itself was becoming more hostile to complex life. And somewhere beneath all of it, the Siberian eruptions continued, releasing more heat-trapping gases into the sky. The planet had entered a feedback loop. It could no longer easily escape. What makes this chapter of Earth's history feel almost apocalyptic is that the world itself had not physically exploded apart. Mountains still stood, rivers still existed, clouds still crossed the sky. To an individual animal surviving day to day, life may still have seemed possible. With that appearance, the conditions allowing large, stable ecosystems to exist were vanishing piece by piece. Earth was no longer functioning like the world these species had evolved for. And as temperatures climbed higher and the atmosphere grew increasingly toxic, the extinction was approaching its most devastating phase yet. There may have been no single moment when life on Earth realized it was losing. No final sunrise before collapse, no dramatic instant where the forests suddenly fell silent all at once. The end of the Permian world appears to have unfolded more slowly and far more cruelly than that. Ecosystems weakened, year after year, generation after generation, until eventually the planet crossed a threshold where recovery no longer seemed possible. By the height of the extinction, the Earth was no longer a stable home for complex life. It had become a hostile system fighting against the organisms trying to survive inside it. The oceans were suffocating. Temperatures remained dangerously high across huge portions of Pangaea. Forests collapsed into dead landscapes. Food chains fragmented. And still, the volcanic activity continued in the background like an open wound beneath the planet's surface, feeding greenhouse gases into an atmosphere already pushed beyond equilibrium. This was the closest Earth may ever have come to becoming a nearly lifeless world since complex ecosystems first emerged. Fossil evidence from the extinction interval preserves a strange pattern that appears again and again across different regions of the world. Biodiversity does not merely decline. It collapses abruptly into simplified ecosystems dominated by only a handful of surviving species. Rich marine environments filled with specialized organisms suddenly become nearly empty. Diverse terrestrial ecosystems give way to sparse communities populated by opportunistic survivors capable of tolerating heat, drought, low oxygen, or unstable food supplies. Paleontologists sometimes refer to these surviving organisms as disaster taxa, species that thrive temporarily inside environmental chaos after more complex ecosystems have fallen apart. Their success becomes evidence of how severe the collapse truly was. Stable ecosystems favor diversity and specialization. Broken ecosystems favor endurance above all else. The Earth was no longer rewarding complexity. It was rewarding survival at any cost. On land, large animals increasingly disappeared from the fossil record in many regions. Predators that once ruled enormous territories vanished alongside the herbivores supporting them. Forest systems capable of sustaining complex food webs became fragmented or disappeared entirely in some environments. Rivers shifted unpredictably through barren landscapes, stripped of stabilizing vegetation. Soil erosion intensified as root systems vanished. In certain areas, floodplains may have transformed into dry, hostile terrain, unable to support the ecosystems that once thrived there. It is difficult to overstate how psychologically different the world may have looked by this stage of the extinction. Earlier, Permian landscapes had still carried signs of ecological richness, even during instability. But near the peak of collapse, entire regions may have appeared biologically exhausted. Fewer large animals, fewer forests, fewer sounds, less movement, a planet slowly emptying itself. And yet, even then, life did not disappear evenly. Some pockets of survival persisted longer than others. Burrowing animals capable of escaping surface heat endured in certain regions. Generalist feeders survived where specialists vanished. Small body size increasingly became an advantage. because smaller organisms require less food, less water, and often tolerate environmental fluctuations more effectively. This pattern appears repeatedly after mass extinctions throughout Earth's history, but during the Permian it reached extraordinary levels because the crisis was so widespread. Survival no longer depended on dominance, it depended on flexibility. Some of the organisms that endured were not the strongest creatures of the Permian world. They were simply the least dependent on stability. The oceans, meanwhile, were entering conditions so extreme that some researchers describe them as partially euphonic, meaning not only oxygen poor, but rich in toxic sulfur compounds. Entire marine food webs collapsed beneath overheated stagnant waters. Reef ecosystems vanished almost completely. Trilobites disappeared forever. Many marine predators lost prey populations faster than they could adapt. Deep ocean ecosystems likely became especially devastated because oxygen depletion intensifies with depth when circulation weakens. Some seafloor regions may have remained nearly lifeless for immense stretches of time. Even after the worst phase ended, marine biodiversity recovered extraordinarily slowly, suggesting the oceans remained unstable long after the extinction peak passed. That detail matters because it reveals how deeply the planet's life support systems had been damaged. This was not a temporary shock followed by rapid renewal. Earth itself struggled to recover. One of the most chilling possibilities is that atmospheric oxygen levels may also have declined significantly during this period. Exact estimates remain debated, but some models suggest oxygen concentrations dropped low enough to place severe physiological stress on large active animals. Lower oxygen means reduced endurance, weaker metabolism, slower recovery from exertion, and increased difficulty surviving extreme heat. In a world already suffering from collapsing ecosystems and rising temperatures, even small atmospheric changes could push vulnerable species beyond survival limits. 2. Imagine predators exhausting themselves more quickly during hunts, herbivores struggling to migrate between shrinking water sources, young animals failing to mature because environmental stress overwhelms them before adulthood. Extinction does not always arrive dramatically. Sometimes it spreads through reduced reproduction, failed migrations, weakened immune systems, and generations increasingly unable to survive conditions their ancestors once tolerated easily. There are moments in the fossil record from this time that feel almost unsettling in their emptiness. Layers of rock that once contained abundant marine fossils suddenly preserve very little life at all. Diverse ecosystems narrow into sparse communities, dominated by only a few hardy organisms. In some terrestrial deposits, the disappearance of certain plants and animals happens so completely that entire ecological structures appear erased. Not transformed, erased. It creates the impression that the Earth had crossed a boundary where normal evolutionary competition no longer mattered because the environment itself had become the primary threat to nearly everything alive. To one especially haunting idea is that the extinction may have unfolded differently depending on where organisms lived. Some tropical regions may have become too hot for many species long before cooler areas failed. Coastal ecosystems faced collapsing oceans, while inland species struggled with drought and temperature extremes. Mountain regions might briefly have acted as temporary refuges, but because the crisis affected atmosphere, oceans, climate, and ecosystems simultaneously, Even surviving regions eventually became unstable. There was no truly safe environment left for long. And because Pangaea connected so much of the planet into enormous continuous ecosystems, collapse spread farther and more efficiently than it might have on a fragmented world. Scientists continue debating whether the extinction reached its worst point rapidly or in several devastating waves separated by short intervals. Some evidence suggests repeated environmental shocks may have prevented recovery each time ecosystems tried stabilizing. If true, many species may have survived initial disasters only to face renewed warming, acidification, oxygen loss, or volcanic disruption before populations could recover. That possibility makes the extinction feel even more merciless. The Earth was not merely killing life once. It may have been repeatedly destabilizing the conditions required for recovery itself. By some estimates, over 90% of marine species disappeared. On land, the losses were similarly catastrophic. Insects suffered one of the few known mass extinctions in their evolutionary history. Forest ecosystems collapsed. Entire branches of evolutionary history vanished permanently. And perhaps the most unsettling part is that many of these species had already survived previous environmental crises over immense spans of geological time. Permian extinction exceeded the adaptive capacity of life that had endured for hundreds of millions of years. That fact alone explains why scientists often describe this event not merely as a mass extinction, but as the Great Dying. Yet, even during the darkest stages, the Earth was not completely dead. That distinction matters because it reveals something profound about life itself. Even under conditions approaching planetary collapse, survival continued in scattered fragile pockets. Small burrowing species endured beneath the surface. Certain marine organisms persisted in oxygenated refuges. Hardy plants colonized damaged landscapes. Microbial life expanded in environments too hostile for larger organisms. The biosphere had been shattered, but not erased. And strangely, that partial survival may have shaped everything that came afterward. Once dominant species vanished, ecological space opened for entirely new forms of life to emerge later. The extinction was not only an ending, it was also a violent evolutionary reset. But standing inside the Permian world itself, none of that future renewal would have been visible yet. To the organisms living through it, the world was simply becoming harder and harder to survive. The skies remained hazy with volcanic gases and dust. Temperatures stayed dangerously unstable. Oceans suffocated beneath stagnant waters. Forests disappeared from regions where they had stood for millions of years. The familiar structure of life was dissolving, and perhaps the darkest realization hidden inside this moment is that the Earth did not collapse because of one impossible cosmic accident. Much of the disaster emerged from interconnected planetary systems amplifying one another until stability itself failed. The atmosphere, oceans, climate, geology, and ecosystems all became trapped inside reinforcing feedback loops that life could no longer escape. The Permian extinction was not simply a disaster happening on Earth. It was the Earth system entering a state where the survival of complex life itself became uncertain. After the worst phase of the Permian extinction passed, the Earth did not suddenly heal. There was no dramatic moment when the skies cleared and life returned to normal. The planet that emerged afterward was quieter, emptier, and strangely unstable, as if the world itself had survived a trauma too large to fully recover from. Entire ecosystems that once covered continents and oceans had vanished. Forests were gone from many regions for long stretches of time. Reef systems that had supported marine biodiversity for millions of years collapsed almost completely. The atmosphere remained harsh. The oceans were still dangerously low in oxygen in many areas. And yet, despite all of that devastation, something extraordinary happened. Life refused to disappear entirely. A handful of organisms endured inside conditions that should have destroyed almost everything. And those survivors would inherit a planet stripped nearly bare. One of the strangest creatures to emerge from this devastated world was Lystrosaurus, a stocky tusked animal that looked almost like evolution had assembled it from unrelated parts. It had a barrel-shaped body, strong limbs, a beak-like mouth, and short tusks protruding from its face. It was not elegant. It was not terrifying. It was not the dominant apex predator people usually imagine surviving an apocalypse. But for a period after the extinction, Lystrosaurus became astonishingly successful. Fossil evidence suggests it spread across enormous parts of Pangaea, especially in southern regions. In some post-extinction rock layers, the majority of vertebrate fossils belong to this single genus. Entire landscapes that once supported rich ecosystems filled with diverse species now appear dominated by only a few hardy survivors like Lystrosaurus. That pattern tells an important story. After a collapse, this severe survival no longer favored the most specialized or impressive organisms. It favored creatures capable of enduring instability. Scientists still debate exactly why Lystrosaurus survived when so many others vanished. Some researchers suspect its burrowing behavior may have helped it escape heat extremes and environmental stress. Others point to its relatively simple diet and sturdy body structure. It may have been capable of surviving on sparse vegetation in damaged ecosystems where larger herbivores failed. Too, there is also evidence suggesting some surviving species during this period had lower metabolic demands, allowing them to tolerate poor environmental conditions better than highly active animals. None of these explanations alone fully solve the mystery, but together they reveal something fascinating about mass extinctions. The traits that help organisms dominate stable ecosystems are not always the traits that help them survive planetary collapse. The Earth after the Permian extinction rewarded endurance over complexity, simplicity over specialization, flexibility over dominance. The landscapes these survivors inhabited may have looked almost post-apocalyptic by modern standards. In many regions, forests appear to have been replaced temporarily by barren floodplains, sparse vegetation, and unstable soils. Fossil evidence suggests fungal growth surged after the extinction, likely feeding on enormous amounts of dead organic material left behind by collapsing ecosystems. Rivers flowing through damaged terrain carried heavy sediment loads because root systems no longer stabilized the land effectively. The sky may still have remained hazy at times from ongoing volcanic activity and environmental instability. The world was alive, but only barely. Perhaps the strangest part is how long recovery actually took. Earlier extinction events in Earth's history were severe, but ecosystems often rebounded comparatively quickly on geological timescales. The Permian extinction was different. Some marine ecosystems may have required millions of years before biodiversity fully recovered. The planet had not merely lost species, it had lost ecological structure itself. The oceans remained especially damaged. Large portions were still oxygen poor long after the extinction peak passed. Reef systems did not immediately return because the environmental conditions supporting them remained unstable. Some surviving marine organisms spread aggressively into ecological niches, left empty by extinction, but diversity stayed unusually low for extended periods. This is one reason the Permian extinction feels so uniquely unsettling. It was not simply a mass death event followed by renewal. It was a prolonged biological bottleneck where life itself struggled to rebuild functioning ecosystems from near collapse. On land, many surviving animals were small compared to earlier Permian giants. This pattern appears repeatedly after extinction events because smaller organisms reproduce faster, require fewer resources, and adapt more easily to unstable conditions. In a damaged world where food chains repeatedly collapsed, being small became an advantage. Burrowing behavior also appears increasingly common among surviving species, possibly because underground environments provided partial protection from heat, UV radiation, or atmospheric instability. Imagine entire ecosystems retreating into survival strategies focused not on expansion or dominance, but on hiding from the world itself. The Earth had become dangerous even to the organisms that survived it. Yet evolution never truly stops. Even inside devastation, new possibilities begin emerging. With so many dominant Permian groups erased, ecological space opened across the planet. Predatory niches vanished. Herbivore populations collapsed. Marine ecosystems fragmented. The extinction acted almost like a reset button on evolutionary competition. Groups that once remained minor or geographically limited suddenly found opportunity in the emptiness left behind. Among them were the early archosaurs, a lineage that would eventually give rise to crocodiles, parrots, pterosaurs, and dinosaurs. At the time, however, there was nothing inevitable about their future success. The post-extinction world was still unstable and dangerous. Survival remained uncertain for nearly everything alive. One fascinating question scientists continue exploring is whether some surviving organisms were not necessarily better adapted overall, but simply lucky enough to occupy environments less affected during the worst intervals. Certain regions may have acted as temporary refuges, where temperatures remained slightly lower, oxygen slightly higher, or ecosystems slightly more stable. If true, then the survival of some lineages may have depended partly on geography rather than purely biological superiority. Mass extinctions do not always produce clean winners chosen by evolution. Sometimes survival depends on timing, location, and chance operating together under catastrophic conditions. That realization changes the emotional tone of the story. The modern world may partly exist because a handful of species happened to endure, while others disappeared forever. There is also growing evidence that the recovery period itself remained ecologically volatile. Carbon cycles fluctuated. Ocean chemistry shifted repeatedly. Temperatures likely remained unstable in many regions. Some ecosystems appear to recover partially before collapsing again under renewed environmental stress. Recovery after the Permian extinction was not a smooth upward climb back toward biodiversity. It was uneven, fragile, and repeatedly interrupted by lingering planetary instability. This may explain why certain post-extinction ecosystems remained unusually simple for such long stretches of time. The Earth itself needed time to become habitable again at large scales. One of the most haunting aspects of this period is how completely alien the world would have felt compared to both the Permian before it and the dinosaur-dominated eras that followed. The giant reef ecosystems were gone. Many iconic predators had vanished forever. Entire forest systems disappeared from some regions. The surviving creatures wandered through landscapes, stripped of the ecological richness their ancestors once knew. It was a biologically diminished Earth, and yet, buried inside that diminished world was the beginning of something entirely new. Extinction events destroy evolutionary history, but they also reshape future possibilities. Without the collapse of Permian ecosystems, later groups might never have risen to dominance. Dinosaurs may never have inherited the Earth, and mammal ancestors may have remained minor background species indefinitely. The Permian extinction was not only an ending, it was the violent opening of a new evolutionary age no organism could yet predict. Some scientists describe the aftermath as a disaster world, an interval where ecosystems were so simplified that surviving species spread rapidly across huge territories with little competition. Fossil records from certain regions support this idea, showing low diversity but high abundance among a few dominant survivors. In many ways, it resembles ecological recovery after modern disasters, where opportunistic species often colonize damaged environments first, while complex ecosystems take far longer to rebuild. But the scale here was planetary. Entire continents passed through this biological bottleneck together, and still, even in such devastation, evolution continued experimenting. Small changes in anatomy, metabolism, behavior, and reproduction accumulated quietly among survivors, struggling through unstable climates and damaged ecosystems. Some lineages disappeared soon afterward, despite surviving the extinction itself. Others endured and diversified slowly over millions of years. The Earth was rebuilding, but not according to any predetermined plan. The future biosphere emerged from countless fragile survival stories unfolding simultaneously across a wounded planet. Perhaps the deepest lesson hidden inside the aftermath of the Permian extinction is how resilient life can be without ever becoming invincible. The biosphere came terrifyingly close to collapse, yet some organisms still endured, but survival carried a cost. Most of the old world was gone forever. Entire evolutionary branches vanished without descendants. Oceans remained damaged. Ecosystems remained fragile. The survivors inherited not a recovered paradise, but a broken planet still struggling to stabilize itself, too. And somewhere within those sparse, harsh environments, new evolutionary forces were beginning to rise quietly from the ruins of the old world, preparing to shape the next great chapter of Earth's history. More than 250 million years later, scientists still argue about what truly killed the Permian world. That uncertainty is part of what makes the extinction feel so haunting. The broad outline seems clear enough. Massive volcanic eruptions in Siberia, runaway climate disruption, collapsing oceans, poisoned ecosystems, and the near destruction of complex life. But when researchers try to reconstruct exactly how those events unfolded, what happened first, what accelerated the collapse, what transformed environmental stress into planetary catastrophe, the story becomes far less certain. The deeper scientists look into the rocks left behind by the extinction, the more complicated the picture becomes. It is almost as if the Earth preserved the scars of the disaster while erasing part of the explanation itself. The Siberian traps remain the leading suspect for the catastrophe, and for good reason. The timing aligns closely with the extinction interval. The scale of the eruptions was extraordinary. The environmental consequences fit many of the patterns preserved in the fossil and chemical record. But even here, major questions remain unresolved. Some researchers believe the eruptions alone released enough greenhouse gases to destabilize climate systems globally. Others argue the direct volcanic emissions were only part of the problem, and that the real disaster began when magma intruded into underground coal beds, methane deposits, and organic-rich sediments. In that scenario, the eruptions acted less like the entire cause and more like the trigger for much larger carbon releases already buried beneath the Earth's surface. If true, the extinction becomes even more unsettling because it suggests the planet entered a self-amplifying environmental chain reaction. One of the most debated mysteries involves methane itself. Methane is an extremely powerful greenhouse gas, far more effective at trapping heat than carbon dioxide over short timescales. Some scientists suspect enormous methane releases may have accelerated warming dramatically during the extinction. The source of that methane remains controversial. One possibility involves frozen methane hydrates buried beneath ancient seafloors. As ocean temperatures rose, those deposits may have destabilized and released massive quantities of methane into the atmosphere. Another theory points toward microbial activity. Certain microorganisms thrive in oxygen-poor marine environments and can produce methane under the right conditions. If warming oceans and collapsing oxygen levels triggered massive microbial blooms, the oceans themselves may have begun generating additional greenhouse gases naturally. In both scenarios, the frightening implication is the same. Once environmental destabilization reached a certain point, Earth's own systems may have started intensifying the crisis automatically. There is also ongoing debate about how quickly the extinction unfolded. Earlier interpretations often imagined an abrupt catastrophe occurring over a relatively short geological interval. But more recent evidence sometimes suggests multiple waves of extinction spread across hundreds of thousands of years. Some fossil records indicate ecosystems collapsed in stages rather than all at once. Certain marine species vanished earlier than terrestrial groups. Some environments appear to recover briefly before deteriorating again. This unevenness has led many scientists to believe the extinction was not a single event, but a prolonged cascade of environmental crises repeatedly destabilizing life faster than ecosystems could recover. If that interpretation is correct, the Great Dying may have felt less like one terrible moment and more like living through an endlessly worsening world. Another mystery involves oxygen levels. Evidence strongly suggests large parts of the ocean became dangerously oxygen poor, but scientists still debate how severe atmospheric oxygen decline became on land. Some models propose oxygen concentrations dropped low enough to place enormous physiological stress on large animals. Others argue the reductions may have been significant, but not catastrophic by themselves. The uncertainty matters because oxygen affects nearly every biological process tied to survival. Lower oxygen means weaker endurance, slower metabolism, reduced reproductive success, and greater vulnerability to heat stress. If both oceanic and atmospheric oxygen decline together, the biosphere may have faced a double suffocation event, unlike anything in later extinction periods. Yet, because the atmosphere leaves fewer direct traces than rocks or fossils, scientists are forced to reconstruct ancient oxygen levels indirectly through chemical clues buried in sediment layers. The Earth left evidence behind, but not complete answers. One especially eerie possibility is that toxic hydrogen sulfide gas escaped from the oceans into the atmosphere during the worst stages of marine stagnation. Modern oceans already contain sulfur-producing bacteria in oxygen-depleted regions, but the Permian event may have expanded these environments globally. Certain researchers believe poisonous gas clouds could have drifted from stagnant coastal waters into nearby terrestrial ecosystems, killing plants and animals while further damaging atmospheric chemistry. Some even speculate these emissions may have weakened the ozone layer, exposing life to increased ultraviolet radiation. Evidence supporting this idea remains debated, but damaged fossil pollen and spores hint that UV stress may indeed have intensified during the extinction. If these theories are correct, the Earth during the late Permian may have become hostile in ways difficult to imagine now. Poisoned seas, toxic air, extreme heat, dying forests beneath skies offering less protection from the sun itself. There are even scientists who continue searching for signs of an asteroid impact connected to the extinction. The idea emerged partly because the later extinction that killed the dinosaurs involved a massive impact event, and because certain geological signatures from the Permian seemed unusual enough to invite speculation. Some researchers pointed toward possible crater structures or chemical anomalies that might indicate extraterrestrial involvement. But unlike the clear global iridium layer and confirmed crater tied to the dinosaur extinction, evidence for a Permian impact remains weak and highly controversial. Most scientists today view volcanic and climate-driven explanations as far more convincing. Still, the persistence of the impact hypothesis reveals how difficult it is for researchers to fully explain a catastrophe of this scale using any single mechanism alone. Perhaps that is the central mystery haunting the Permian extinction. No explanation by itself feels completely large enough. Some researchers now suspect the extinction resulted from several overlapping disasters interacting together. Massive volcanism destabilized climate. Warming oceans lost oxygen. Methane releases intensified greenhouse effects. Ocean chemistry shifted toward acidification. Toxic bacteria spread in stagnant waters. Atmospheric systems weakened. Ecosystems fragmented. Recovery failed repeatedly. In that interpretation, the Great Dying was not caused by one event. It was caused by the Earth system crossing a tipping point where multiple feedback loops reinforced one another faster than life could adapt. And because planetary systems are deeply interconnected, once enough feedback loops activate simultaneously, collapse can accelerate in unpredictable ways. There are moments when studying the Permian extinction begins to feel almost philosophical rather than purely scientific. The deeper researchers investigate, the more the disaster reveals how difficult it is to fully understand planetary systems even after centuries of geology, paleontology, chemistry, and climate science. Scientists reconstruct this ancient catastrophe using fragments, isotope ratios preserved in stone, microscopic fossils buried in sediments, chemical traces inside ancient oceans, volcanic layers spread across continents, damaged spores preserved in rock. Each clue reveals part of the story while leaving gaps elsewhere. The extinction happened so long ago that entire mountain ranges have risen and eroded away since it occurred. Oceans opened and vanished. Continents drifted thousands of miles. Much of the evidence has been destroyed by time itself. What remains are incomplete signals from a world almost erased. And yet those signals continue telling a remarkably consistent story about instability spreading through the Earth system at terrifying scale. One especially fascinating question involves whether the extinction pushed the planet close to a true runaway greenhouse state. Some researchers argue temperatures rose high enough to threaten large portions of complex terrestrial life directly. Others believe feedback systems stabilized before the Earth crossed irreversible climatic thresholds. The distinction matters because it determines how close the biosphere may actually have come to total collapse. The Permian extinction already represents the deadliest known extinction event in Earth's history, but there remains uncertainty about how much worse it could have become if warming, methane release, and ecosystem collapse had continued unchecked for longer. There is also the mystery of survival itself. Why did some organisms endure while others vanished forever? Why did certain lineages collapse completely while relatively simple creatures survived and later diversified? Scientists can identify broad survival patterns: small body size, adaptability, burrowing behavior, tolerance for harsh conditions, but no single rule fully explains survival across every environment. Chance likely played a role alongside biology. Geographic luck may have mattered, timing mattered, environmental refuges mattered. The modern biosphere may partially exist because a handful of species happened to survive long enough for conditions to stabilize again. That realization changes how the extinction feels emotionally. It stops seeming like a clean evolutionary transition and starts feeling fragile, almost accidental. Perhaps the most unsettling mystery of all is how familiar some aspects of the Permian extinction appear when viewed through the lens of planetary systems. Rapid greenhouse warming, ocean acidification, oxygen loss in marine environments, ecosystem collapse spreading through interconnected systems. Scientists are careful not to treat the ancient extinction as a simple direct parallel to the modern world because the scales, timescales, and causes differ enormously. But the Permian event demonstrates something profoundly important about Earth itself. Once enough environmental systems destabilize together, recovery becomes incredibly difficult. Stability is not guaranteed. It emerges from countless interactions operating in balance, and balance can fail. The Great Dying remains unfinished as a scientific mystery because Earth's systems are too large, too interconnected, and too ancient for any one explanation to feel entirely complete. Every layer of rock reveals more detail, while also exposing how much remains uncertain. The extinction destroyed most life on the planet, yet the exact path from volcanic eruptions to near global biological collapse still contains unanswered questions hidden inside deep time. And perhaps that uncertainty is fitting. The Permian extinction was not merely a disaster. It was one of the rare moments when the Earth itself became almost unrecognizable, a world so unstable that even now, hundreds of millions of years later, humanity is still trying to understand exactly how close life came to disappearing forever, too. When the worst phase of the Permian extinction finally began to fade, the Earth that remained was almost unrecognizable compared to the world that existed before it. The great forests of the late Permian were gone from enormous regions. Reef systems that had flourished for millions of years had collapsed into silence beneath depleted oceans. Entire branches of evolution vanished forever without descendants. The planet was still alive, but only in the way a burned forest is technically alive after the fire has passed. A few organisms remained. Some ecosystems persisted in damaged fragments, but the old world was over. And perhaps the strangest part of this story is that everything familiar about later Earth history, the rise of dinosaurs, the evolution of mammals, the eventual appearance of humans, may have depended on that destruction happening exactly when it did. Without the Great Dying, the modern world might never have existed at all. The extinction did not merely erase species, it rearranged the future of life itself. In the millions of years that followed, the Earth entered the Triassic period, an era that began not with thriving ecosystems, but with biological emptiness. Fossil records from the early Triassic often show surprisingly low biodiversity compared to both the Permian before it and later periods afterward. Many environments remained unstable. Ocean ecosystems recovered slowly. Atmospheric and climate systems likely continued fluctuating long after the extinction peak passed. Some scientists believe portions of the Earth remained dangerously hot for extended intervals, making recovery uneven and difficult. The biosphere had survived, but it had been fundamentally weakened. This slow recovery is one reason the Permian extinction feels so different from ordinary extinction events. It was not simply a reset followed by rapid rebirth. It was a prolonged struggle for life to rebuild complexity on a damaged planet. The surviving organisms inherited a world filled with ecological vacancies. Predator niches stood empty. Herbivore populations had collapsed. Marine ecosystems lost countless dominant species. In stable ecosystems, evolutionary competition can limit the expansion of new groups because most ecological roles are already occupied. But after the Permian extinction, huge portions of the biosphere were suddenly available. Entire evolutionary pathways opened at once. This created opportunities for surviving lineages that previously existed only at the edges of ecosystems. Among them were the early archosaurs, the broader group that would eventually produce crocodilians, flying reptiles, and dinosaurs. At first, they were not rulers of the Earth. They were simply survivors moving through a biologically shattered world, searching for opportunity among the ruins. That detail matters because the rise of dinosaurs was not inevitable. It depended on countless earlier species disappearing first. The Permian extinction removed ecological barriers that had existed for millions of years. Dominant synapsid groups collapsed. Marine ecosystems reorganized. Food chains rebuilt themselves around surviving lineages rather than older established systems. Evolution does not plan ahead. It reacts to opportunity. And the Great Dying created more evolutionary opportunity than almost any event in Earth's history. The extinction acted almost like a massive biological bottleneck, forcing life through an extraordinarily narrow filter. Everything that emerged afterward carried the imprint of survival through catastrophe. One of the most fascinating consequences of the extinction is how it reshaped evolutionary strategy itself. Many surviving groups favored traits associated with resilience rather than specialization. Smaller body sizes became common after the extinction because smaller animals often reproduce faster and require fewer resources. Flexible diets mattered more than narrow feeding specialization. Burrowing behavior helped protect against unstable climates. Heat tolerance became increasingly important. Post-extinction world rewarded adaptability because environmental conditions remained unpredictable for immense periods of time. In some ways, the Triassic Earth became an evolutionary testing ground where only organisms capable of handling instability could expand successfully. The oceans also rebuilt themselves almost from scratch. Reef ecosystems eventually returned, but not in the same forms that dominated before the extinction. Marine food chains reorganized around surviving groups and newly evolving species. Entire ecological structures changed. Some ancient lineages never recovered at all, while other groups rapidly diversified into newly available habitats. Even the chemistry of the oceans may have remained unstable for long intervals before marine systems fully stabilized again. This drawn-out recovery reveals how deeply the extinction damaged the Earth system itself. The biosphere was not merely reduced in numbers. Its internal complexity had been shattered, and complexity takes immense time to rebuild. There is something strangely humbling about realizing that the Earth humans know today emerged from such fragile survival. Mammals themselves descend from synapsid ancestors that barely survived the extinction bottleneck. If a few key lineages had vanished completely during the Permian collapse, mammals might never have evolved at all. The entire history of primates, human civilization, cities, languages, and technology may ultimately trace back to a handful of creatures enduring one of the harshest planetary crises ever recorded. The modern world exists partly because extinction did not become total extinction. That realization changes the emotional meaning of deep time. Human history often feels enormous from a personal perspective, but against the backdrop of the Permian extinction, civilization becomes a very recent consequence of much older survival stories hidden inside the fossil record. Some scientists describe mass extinctions as both destructive and creative forces. That wording can sound unsettling because it risks making catastrophe feel purposeful when it was not. Permian extinction was not a planned transition preparing Earth for dinosaurs or humans. It was a planetary crisis that nearly erased complex life altogether. Yet, once the old systems collapsed, evolution inevitably began exploring new possibilities among the survivors. Extinction clears ecological space. Evolution fills it again. Biosphere that emerged afterward was different because the organisms capable of surviving the catastrophe were different. In that sense, the Permian extinction permanently altered the direction of life on Earth. Even today, traces of the disaster remain visible in modern ecosystems. Entire groups of organisms dominating before the extinction are gone forever. Reef systems rebuilt differently. Marine biodiversity followed new pathways. Terrestrial ecosystems reorganized around surviving lineages rather than older Permian dynasties. Earth history, after the Great Dying, became the history of a biosphere recovering from trauma. And perhaps the strangest part is how invisible that trauma would eventually become. Millions of years later, dinosaurs would dominate lush ecosystems across thriving continents. Mammals would diversify quietly beneath them. Flowering plants would spread across the planet. Birds would fill the skies. Oceans would teem with new marine life. The Earth would appear stable again. Yet buried beneath those later worlds remained the geological memory of a time when life nearly failed completely. There is also an uncomfortable modern resonance hidden inside the Permian extinction. Though scientists are careful about drawing direct comparisons, the ancient world and the modern world differ enormously in time scale, causes, and biological contexts. But the Great Dying demonstrates something profoundly important about planetary systems. Climate, atmosphere, oceans, ecosystems, and geology are deeply interconnected. When enough systems destabilize simultaneously, recovery becomes incredibly difficult. Ocean warming affects oxygen levels. Ecosystem collapse affects carbon cycles. Atmospheric changes alter climate feedbacks. Nothing exists in isolation for long. The Permian extinction remains Earth's clearest warning that biological richness alone does not guarantee stability forever. The planet can become hostile, surprisingly fast, once enough feedback systems intensify together. And perhaps that is why this extinction still feels emotionally different from other prehistoric disasters. The asteroid that killed the dinosaurs was sudden and violent, but the Permian extinction feels slower, heavier, more existential. It was not merely destruction arriving from outside the Earth. It was the Earth system itself unraveling from within. Oceans suffocated, forests collapsed, atmospheres changed, heat intensified. Life retreated into scattered pockets while the planet struggled to remain habitable. The Great Dying was not only an extinction event, it was a test of whether complex life could survive a world where the normal balancing systems of the Earth stopped functioning properly. Somehow, against overwhelming odds, some life endured, but survival came at the cost of almost everything that existed before. Today, when scientists study ancient rocks from the Permian-Triassic boundary, they are not simply looking at fossils. They are looking at the remains of one of the most important turning points in Earth's history. Without it, dinosaurs may never have risen. Without dinosaurs, mammals may never have expanded into dominant ecological roles. Without those mammals, humans almost certainly would not exist. The Great Dying destroyed the old world so completely that it accidentally opened the path toward another one. And perhaps the most haunting realization of all is that none of it was guaranteed. Life survived because enough systems stabilized before total collapse became irreversible. The Earth eventually recovered because feedback loops that once intensified catastrophe finally weakened again over immense spans of time. But the Permian extinction proved something permanent about this planet. Stability is not fixed, ecosystems are not immortal, and even a world overflowing with life can drift frighteningly close to silence before anyone inside it realizes how much has already begun to disappear. Thanks for spending this time exploring Earth's deadliest extinction with me tonight. If you enjoyed this journey into the ancient world, don't forget to subscribe and let me know what prehistoric mystery you'd like to explore next.